Hello everybody. So in this video I'll introduce you to a new topic, and that is how we can find the length of a polar curve. Okay, so in order to really understand that and do these questions reliably, we have to understand what polar coordinates are, and we have to understand what some basic graphs are in polar coordinates, and if we don't recognize the graph as something, how to graph it. Now, I've made other videos on that, so I'm not going to go back over it here, but if that's an issue, you can look back on the material I provided for polar coordinates. Okay. All right. So, but let's assume we know polar coordinates by now. Some of what I do here, I hope will enrich your understanding of polar coordinates already. But how about this? Let's just see how this sort of thing works and learn how to solve it. So it says this: find the length of the following polar curve. I'm given a curve in polar coordinates that involves r and theta, and I want to know like some distance. It says length. Okay, so let me tell you how that scenario is going to look in general. So we've got some curve in polar coordinates. It'll involve r and theta because that's what polar coordinates are. Let's say this curve looks like this. Just kind of goes through space like that, two-dimensional space. And we look at just a part of it, let's say, from theta is equal to angle A, which directs you to this point, over to theta is equal to some other angle B, which directs you to this other point. Now, if I were to travel along this curve between those points, I would have to go a certain distance or length, and that's what we're trying to measure with this sort of question. Okay? Now, let's say that I get some equation in polar coordinates. R is a function of theta. Okay, that means that r is expressed as some formula that involves theta in it. You can find the distance as indicated here like this. Angles A and B are your boundaries. They define a segment or piece of that polar curve. They will be the bounds for your integral. And then we have root f prime theta squared plus f of theta squared. F of theta being this original function squared, and f prime being its derivative. Okay, so that's how we'll do it. Now, let's apply that to this question. It says, find the length along the following polar curve. Now, in this question, it means the whole length, like the distance to go all the way around it and back where you started. So we might have to adapt this a little bit. I've made this look like, well, we just have like a little piece of a polar curve, but this is a circle, and what it's asking us is, if we were to start here, how far would it be to go all the way around the curve with the shape that it has back to where we started? Okay, that's what it's asking us. Now, it would help to recognize that r is a sine theta, where a is some constant that's positive, is a circle. It has a center on the y-axis with xy coordinates 0 for x, a over 2 for y, and it has a diameter of a. So here I've drawn a circle like that. Okay, so for example, like if it has a diameter a, then this point theta is pi over 2 or 90 degrees, directs you to some point that's directly on the y-axis somewhere. According to this formula, sine pi over 2 is 1 times a is a. That gives you an r coordinate of a. Okay, so that gives you a diameter for the circle of a with its center there on the y-axis. Okay, now I've just kind of mapped out a few points. You know, if theta is 0, you're directed to be at some point along the x-axis. Well, that's this point down there. If theta was pi over 4, for example, 45 degrees, it would direct you to this point. And for theta being pi over 2, it would direct you to this point. So I could say this. I could say, yeah, as theta increases, you just get these points along this circle until you get all the way to pi, and then you get back where you started. So, okay, let's do this. As I've tried to explain it, I want you to see this about it. If you let theta run from 0 to pi over 2, you'll get half of the distance that we want. Okay? You won't get all of it, you get half of it. All right. So, why don't we do it like this? I want to do this with symmetry. If I find bounds that will get me half of what I want, I could answer like so, and I could double my answer. Now, why would I do that? Well, because I think we'll see in some other questions that we might not want to use the entire bounds for whatever distance we want, but maybe just a part of it and then use symmetry to doubling it to get our answer. So here, just because I think it could come up in other questions, I want you to humor me and see that, okay, yes, if theta runs from 0 to pi over 2, that will get you half of what you want. Okay? All right, I'll set it up that way. So if this is the integral that gets you the answer, the arc length, then we will double it. Our bounds will be 0 to pi over 2, root f prime theta squared f of theta squared d theta. F of theta is a sine theta. Its derivative, since a is a constant, is negative a cosine theta. So I put that in here. Okay? All right. Then I realize, well, I've got to apply this exponent here, this square. I get a squared cosine squared plus a squared sine squared. Then, as will often be the case when we're working with polar coordinates, I see that there's going to be a trig identity that comes into play. I see cosine squared plus sine squared, which is 1. If I factor out that a squared, I get a squared times cosine squared plus sine squared. That's a squared times 1. That's just a squared. So under that root, as complicated as this seems like it was going to be, it's just a squared. Now, the square root of a squared is a, if you know that that number is positive. If you don't know that a is a positive number, then this can't be done. So it is positive. That was given to us from the beginning. All right. And I get root a squared is a. And then that's a very easy integral to work from here. What is the antiderivative of the constant a with respect to theta? It'd be a times theta. Bounds pi over 2, 0. Put pi over 2 and 0 in. Multiply by 2, I get a theta. Okay, so there's your answer. The distance all the way around this is a theta. I set up an integral whose bounds would give me half of that, and then I doubled it. I just wanted to see that that is doable and that would work for this one. Okay, it's not that I have to use symmetry and set it up for half and double it in this one, but like I said, I think we'll encounter situations later where we might need to do that, so I want you to see how it can be done here. Now, you might have wondered as I've done this problem, all this is asking for is the circumference of this circle, which does not require calculus to do. So why did I use calculus? Well, I did want to show you this concept and the integral that will measure what we want. But yes, I agree. It's that you don't have to use calculus. It's not the only way to do it. So how about this? Let's see. I used calculus. I used this concept of the length of a polar curve to find my answer. Calculus is not necessary to solve this problem. Can we confirm the answer without calculus? Let's summarize the problem like this. We have r is a sine theta. That is, however you see it, polar coordinates or not, that's a circle of radius a over 2. Over here, this distance right here, from here to here, is a. It's got a diameter of a, so it's got a radius of a over 2. And what I understand the problem to be asking for is what's the circumference of the circle? And there's a well-known formula to tell you that. The circumference of a circle is 2 pi times the radius. I know the radius. So it's 2 pi times a over 2. The 2's cancel. I get a times pi. I get the same answer. It's confirmed. So yeah, we don't have to use calculus to solve this. I think actually, if you're doing the assignment and you read a question and you understand it so well that you see it's just basic geometry, such as finding the circumference of a circle, then you can do it that way, not needing to use calculus and integration and something that might be very complicated. Okay, but I would like you to get to the points with polar coordinates that you can read this question, you can understand it's just asking for basic geometry. But we'll find questions where that's not possible and we will need to use an integral like this. Okay, and you see this setup here, and my work was applicable to the answer to that question. All right, so that's my first video to introduce length on a polar curve. There will be some others where we might have to concern ourselves with symmetry, adjusting these bounds, possibly doubling the answer as needed.